Thank you very much for the kind introduction. So hello everyone, thanks for coming. As I said, as Joshua said, I will present to you today the Demeter Metamorphosis library, which I worked on for the past years. I started it during my PhD with Joan Glones and Pietro Gori, and so now I'm in the postdoc, and I'm working with Alain Trouvé. So why should we use Demeter? Demeter is, you should see it for now just as a registration library, like image registration library. And especially as it is implementing Metamorphosis, and I will come back on the definition and stuff of Metamorphosis, it is made for registering image with different topologies. Okay, so it is made for 2D images, 3D images, and especially MRI. It is a Python library based on PyTorch for GPU support and auto differentiation. And it's also a very modular library made for doing some different kind of models of metamorphosis. And so it allows you to do a lot of stuff, and I will show you today how. So it's a very young library, a few years, but I was a lonely developer, and I had to learn a lot of stuff. So please, I'm eager to have your feedback. And if you want to leave me an issue, there is a section on GitHub for that. And I will be happy to hear from you and to read you. So today's presentation. So it's a software tutorial. I will start by the 15 minutes presentation that I already started. And then we will have like 35 minutes about something for you to try the library. And for that, I prepared you some stuff. So you have access to these slides. They are on the GitHub page. So there are 2D slides. Yeah, so it's a bit different than the thing you are used to. So on the first level, the first row, you have all the theory and all my talk, all the thing I will talk to you about today. And if you see an arrow down here, that means you have something more material to read about the library, or a mission. If you accept the mission, you can try it out for yourself. And so they are marked as well with the symbols, so the little file with a key or the mountain. Okay, so just before you start using, I know that we implemented together, but there was some bug fixing since. It's ready now, but you just have to update it, and you just have to run the command in your terminal. It should be straightforward. And if not, I can help you at the end of the presentation. Okay, we're now ready to start the actual theory and stuff. So metamorphosis, to understand it, you have to understand what is LDDMM. LDDMM is a registration method that I'm using on images, but you can use on any kind of data point. And it's for doing a temporal non-linear registration. So here I have an example of an interpolation between two brains here. You have a target brain, and here you see the comparison in between the source and the registered, like the target and the registered brain. So LDDMM allows you to compare shapes with, compare two shapes with deformation. So here we have an example that kind of stopped. But so you can compare the two fishes. So it's kind of the classic example of Darcy Thompson. And actually, the video works on my computer, but not on the screen. That's unusual. All right, but so here you should see a deformation grid here that compare the two images. Okay, so how do we model the deformation in LDDMM. So it's a flow of vector fields. We just take the derivative and we integrate over the V, which are the vector fields. We want all the vector fields to be part of an admissible vector space. I choose the representation, the reproducing kernel representation. So we just define reproduction kernel. So here, for example, there is the Gaussian one, and it will allow us to define the V-norm, which is defined through the inverse of the kernel, L going to the dual space. Obviously, with the Demeter, I defined it. I implemented all the kernels, so there is few for now. If you feel that something is missing, you can do it yourself as well. Okay, so I talked about deformation. Now we have to talk about how they are implied on images. So the deformation group, the deformations form a group that can act on images as well. So we have here we see the image transport, that is the advection as well in fluid dynamics. So we have the partial derivative in time of the image E, which is just scalar the field and the gradient of the image. And you can also apply the image, like the deformation on the image, with the inverse deformation on the image. It's a bit the reverse than we are used to if you are used to point clouds, but that's how we do it with images. We can define geodesics on the spaces, on the deformation space and on the image space. And this is just with the Riemannian metric integrating over the V norms that I defined it earlier. And with all of this, we have a distance in between images, which is the great strength of LDDMM. Okay. So LDDM is a very nice tool. However, it can register only images with same topology. So like all the ones that share the same orbits, the same can be registered together with LDDMM. But if not, we have to break the topology somehow. And so that's why that's what Metamorphosis is for. And so here the image C on the far right, far left, sorry. You have like the C image that was cut, and there was a point appearing. So the topology in between C and B are different. And so that's where Metamorphosis comes from. And so you have the LDDM part, a bit a different thing, but we have in the equation on top, you can see in red the LDDMM part, the transport part, and we add some Z, which are intensity differences in the image. And we want to do something like a somewhat a barycenter in between the two things, like a weighted sum in between the deformation and the registration, and the intensity difference. Okay, so just to give you some examples before we dive a bit more in Metamorphosis and how I implement it. So you have the source image, a target image. If you use LDDMM, you have quite a good registration. However, if we compare it with the target image here, you have the cut in the target image wants to be explained with deformation, which is not what we want to have. And so we have a very big deformation here. It's done. It is doing what we want to, what we ask him to do, but. And Metamorphosis here can do a way cleaner registration, deformation-wise, with some intensity that are added, like at the cut and the round. Okay, so now some implementation details, how I did it. Just to give you the formal definition, I said you that you can define LDDM as a path on the shape of diffeomorphism. Metamorphosis is the same, so it's just a two paths cross. And so you have a path in the deformation and one on the intensity changes. So the notion of geodesic and Riemannian matrix stands. How do we register in practice? So first, we have to determine the expression of a geodesic. So we will compute the equation of the geodesic, and in an exact matching setting. And then we will relax the problem in exact matching and doing some geodesic shooting. I will be a bit more precise now. So for the first part, the geodesic thing. So we model, we say, okay, I want my image to evolve like this. So the first equation, the partial derivative of I. Then we define the Hamiltonian. So this is the energy. We have the V norm. We want to add the less intensity changes possible. So we have the norm 2 on Z. And then we compute we compute the geodesic using the Noether theorem and stuff. And we get this kind of geodesics here. So I won't get too much into the details, but just to see, we have here the continuity equation for the momentum. P is the momentum. And here we have the advection equation with the source term. And so that's somehow related with some 3D dynamics equation. And so here I just integrated over a geodesic. I started in a random direction, and we have not so random direction, but yeah, and we just evolve it following it. And so we have this kind of fluid dynamic evolution.
Some effects that appear. So what is the boundary value problem that you're solving here?
So here, it's not really a problem I solved.
It's initial value problem?
Yeah, I just took a round image at the start of the animation, and I put it some. I set an initial momentum that say, okay, goes a bit to the top, and just integrate it over some time without thinking too much, and so we have this kind of result. Just pretty kind of. But then, with the second part, it becomes useful. So okay, just some details. I will go fast because I only have 2 minutes left. So just the point of the slide is to say that I can make my cost a bit easier, losing the integral and optimizing only on the initial momentum, which is P0 here. And this is because of the Noether theorem, and that if I follow a geodesic, the norms should be constant over time. Okay. So now the geodesic shooting phase. So we take a P0 initial momentum. We do the geodesic integration with the equations. We get an image at time 1. We plug it into a data cost. So we relax the problem, the exact matching problem, with a data cost. So here E1, here I put the SSD, and then integrate over this thing. So we have here a regularization cost, and here the data cost. So the gradient is automatically computed with PyTorch and the auto differentiation of PyTorch. We should use semi-Lagrangian schemes. I don't have time to just go on the details here, but you can watch yourself on the slides. And so just to give you an example, one of the aim of my thesis was to reduce to this kind of images. So you have kind of a very, very blend simulation of a brain and a cancer that grew inside of it. And so we expect the oval gets to the round and the little gray organs to be matched and something appearing at the center. So if you use Metamorphosis, we see that it don't work so good. So if we use rho equal 1, we have like LDDMM, which is there is no topology differences, And here we see that we have appearance and deformation. However, it's not really the way we intended to. And that's because we have to fix the balance in between the parameters. And so that's why like the next iteration was to add a mask to control locally this parameter rho. And so there are smooth masks, temporal masks, going from 0 to 1. And we just interchange the rho with the mask here, and we get some very similar equations like we had before. So I just comment here. One of the missions you'll have to do today is to reproduce this result. So you want to have a registration that looks like that at the end. And here you see the residual, so the ZT, that appearing and shows exactly where we want to have some intensity changes and how they evolve in the image. And so you can find on the GitHub at this link, you can click on the link and you'll get the example, which is a bit preprocessed. And so you have to fill some blanks. Okay, and just before I end, weighted metamorphosis is nice. However, it's maybe not enough. And there is another model that is called constraint metamorphosis. And the idea here is, okay, I have a temporal mask, why not? But maybe I have also some priors on the field, on the direction. I don't know if you have a rotation or something. And so I just add a term here in the metamorphosis cost Hamiltonian, which with if I have a W cost that I want to follow at location given by Q a matrix, a weight matrix, I want to follow W here. And so it's changed the equation just a bit, adding the W into the expression of the vector field that we want to estimate. And so the last mission you'll do, if you accept the missions, obviously, is to do this registration. So it's a very hard one. With like it's almost accurate to example for a cancer. We have a big necrosis, very intense at the center. Some edema appearance that I don't know if you can see here on the slide, but it's a bit more clear around the thing, but not inducing deformation. And you want to get a registration that looks like that somehow at the end, with the residual that explains really what are the intensity differences in between the images. And so you can see the complete example here again on the GitHub. So thank you very much for your attention. And now I'm here with you to help you to do the different missions, to find anything you can ask me. You can ask me anything. So again, don't hesitate. If like some of you have some interesting remarks and yeah. So don't hesitate to put them in the GitHub. I would be really glad to solve this problem. Okay. And for me, it was very good to see how you behave on this. So just a bit slow. Okay, so you should see now my screen. Okay, it's terribly slow to just close a window. So I don't know how it will happen, how it will go. Come on. No, I pressed it like 100 times. Okay. Okay, so we are on this file that builds the toy example. So this is the hard example. I just okay. So we have this. Sorry. Ah, yeah. Okay. Yeah, it's too small, obviously. Can I zoom? I can zoom. Is it big enough? Okay, good. Sorry. Why it's not working? Okay, I did. So we first want to just display the images quite quickly. So I open them. I have we have that the masks. Later. What? Then we want the masks are actually used for validation rather than. I just defined here a multi-scale Gaussian kernel. You can see the details on the documentation here. So I put two levels of sigma, which are 10 and 15. My image is squared, so. First, here in this, I will do a first mask. How I do my mask? I will use LDDMM to register two shapes. So just look at this. Didn't make pale good. Okay. So first, I want to take an initial ball like this. Yeah, and I want to deform it on the big necrosis banana. And so we can see that here, like with LDDMM, I did the registration quite easily, and I have here a deformation field that is concentrated around the banana shape. Then I want to make another mask for the residuals. So here I just had the segmentation of the cancer and the edema. I initialized here a small ball that I just put it in the center of the shape somehow, and deformed it to the shape of the edema and cancer using LDDMM. So here we can see the result. I will show you the result here with the vector fields and the end results. Okay, and now we start like really. So we have evolving masks. We match the segmentation, but we have to tweak a bit the different masks that will really apply, because like for example, if you remind in the equations, If we put row to 1, we have only deformation. So here in the image here, the black means 0. So that means that here in the outside, we have no deformation, which is, so we want the other way around first. So here we will start working with the residual marks. But for now, if I just apply this, so we have already so we have this residual mask that is here. We can see it on the bottom. That is evolving over time, but we want at least to inverse it. For that, it's quite easily. And we just see what happened. I just reverse the mask, and we can already try what happened if we do that. I just show the cut, like the cut of the mask. I smooth it afterward as well. Not obligated, but I did it. And so here I define another reproduction kernel with and so I just apply constraint metamorphosis. Constraint metamorphosis here, you can use it like quite easily with the wrapper method. You took the source, the target, initial momentum. Here it's just 0. I didn't put too much thought into it. Then I will give the mask and field and other constants like the number of iterations I want to integrate over, grad coefficient, the cost constant, with like normal optimization and stuff. So if we try the optimization, so now it's doing live on my computer, and we can see the SSD increasing. I use the SSD for this one because it's a good metric for this example. SSD, sorry, is the sum square difference, which is just you take the integrated image minus the norm 2 minus the target. Okay, so we have the evolution here. And if we want to compare the two images, what happened here? We have a very good looking results here with some vector fields. But if we look at the, sorry, I didn't make it. Oh. If we look at the deformation here, what will happen? Okay, so here what I'm showing is the deformation field, the deformation grid here, the source image, and here the target image. And we have here we see that these little organs wanted to be matched with the very intense edema part. And so that's what usually happens actually when you do a metamorphosis with some kind of different objects that are interlacing. So that's why we wanted to add a field to say, no, I don't want you to go there. We had already fields because we use LDDMM to register images. So we just can use them as a prior. Oh, okay, let's go back to the masks. I remind you, so I just show you again. So we have this mask, which is actually quite good for the residuals. But now we want to do something a bit smarter for the orienting field. And so actually, here I put it 0, but let's do something else. I will start by just saying, okay, where do I want to follow my field? Like if I put my mask to 1, okay, let's try just to put my mask to 1. Okay, so now it's 1 everywhere. It's just like I will follow my mask, the field wherever I want. What will happen? Actually, what do you think it will happen? Yeah, so we did another mask here, which is this one, the necrosis mask, and I just take the vector fields from this one, the temporal vector field, and I want to follow it, kind of. So if I just show the equations again, maybe that will help you. Here. So now I have my new vector field V, W, that I want to follow. And I just want to, so what will happen now if Q here is only once? So, yeah. And so actually, so Joshua said that we will kind of follow the fields everywhere. And so here, where the field should be 0, we will also have like the deduced field to be 0. If I won't do it because I don't have too much time, but what basic solution here is just to take the mask first as a function of the norm of the vector field, or the induced vector field. So if it's 0, I just don't want to follow it. So I just do this thing, num v2, which is this. We just take out. So I want the oriented field that I have. Field. I want to have it squared. And I want to sum it on the last dimension, which is actually the vector. So I take just the norm of individual vectors, and then I just apply the square root of a. We can already show the norm v here now. Okay, so yeah. Okay, so now we just see that the norm here looks like that for the first step, for the first at first time. Okay, so it seems legit. But okay, we want to have the norm too, but now here I don't see the values here, but if we plot just the max, I think it won't be 1 because it's not plant, it's print that I wanted to do. So the max is almost 5. I will just normalize it in order for it to be easier to work with. Okay. And so we can try to just pass it this. But we say that the oriented mask now is the norm V2. Okay. Yeah, because I need to do something here. It's to keep the dimension. No, it's not that. Is that? Is it? Okay, now it's working. So I did some technical stuff. I won't detail too much, but So here now the mask here, the mask over the field, it looks like that. So we see really like the growing happening. I will just bigger, and we see that there is like this two ends here that are kind of converging. Okay, let's try to see what happens if we do that with SSD. Have to wait a bit. It's way faster than it was, but still it takes few seconds for this on the GPU, obviously. If you are doing on CPU, it's okay. So we see that already the landmarks show us that something wrong happened, and the mask evolution, like it converged, but the results do not look good already from the. Okay, so what happened here? What happened here is that the field that we followed was way too big. So we destroyed kind of our. So just to do that, what we can do is to make our oriented mask a bit smaller. I will just cut it at one point. I will say, like, for example, I will put it. I won't make you I won't show it live, the tweaking of the mask here, but we have oriented mask. We have basically the same mask, but cut it here. So it looks like a blob, but it's way lower. And if we applied this, okay, so already we have a way better SSD that we had before. And to get something which is whenever we will see, I will conclude. Second left. Okay, so the optimization graph looks good. The end result here looks good, so but it was like the first time we tried. If we look at the deformation now, we see that the deformation is the one we expected. So we have a big deformation here. We follow the field, the prior field. We have so here, this is the image only deformed without intensity changes. So we see that the organs are well matched. And here there was a big thing that happened. It's where the cancer appeared. Just let's see the evolution time. So you can see here the deformation appearing and the mask growing and stuff. And the last thing, maybe it's just to see where the mask is on the image at each time step. Okay, so that's conclude my talk. So if you have last questions, we'll be happy to answer.